Greetings, colleagues. My name is Ryzhov Anton. Today, on behalf of our Laboratory of Information and Communication Technologies based on dynamic chaos in Kotelnikov Institute of Radio Engineering and Electronics of Russian Academy of Sciences, I'd like to introduce you to our work, Artificial Radio Lighting using sources based on dynamic chaos. Observation of objects using incoherent microwave radiation have been used in radio astronomy, observing the Earth from space, and in medical diagnostics. However, it is important to note that incoherent microwave radiation in these scenarios was the result of natural processes such as intrinsic thermal radiation of physical objects in microwave range or scattering microwave radiation created by powerful natural sources. The idea of radio lighting using local artificial sources that are similar to artificial sources of light in visible range was considered in the literature as an exotic one due to the lack of compact and efficient sources of noise-like microwave radiation. One of the main development direction of our laboratory is the creation of dynamic chaos generators. Our research in this area led to the possibility of creation of compact and energy-efficient noise-like sources of microwave radiation that allowed us to proceed to the investigation of Radiolite. Radiolite is an artificially created noise-like wideband incoherent in time and space microwave signal. Upon reaching the nearby surfaces and objects, microwave radiation is partially consumed by them, partially passes through them, and partially reflects, which is why this radiation during its propagation bears the information within it about the media it interacts with. In general, the situation resembles the one concerning visible light. The main difference is that here we deal with the other frequency band and the other laws of interaction with the media where the process occurs. Here you can see illustrations of the main Radiolite features. This is a deterministic noise-like signal, fragment of which you can see on the figure A. Figure B shows its ultra-wideband power spectrum in the range from 3 to 5 GHz. Autocorrelation function of chaotic signal is a fast decreasing function. The distribution of instantaneous values of chaotic signal resembles Gaussian distribution. All these characteristics of chaotic signal are similar to the ones of visible light that allows us to use chaotic signal generators in the same way that we use usual light sources. Dynamic chaos integrated circuits that includes dynamic chaos generator were developed in our institute. Just like the LEDs are effective source of wideband radiation in visible light range, chaos-integrated circuits are effective source of wideband radiation in microwave range. We had several stages of development of Radiolite sources. On the first stage, dynamic chaos-integrated circuits were made. You can see that on the first picture. After that, there was created the first prototype of Radiolite source with antenna. And finally, a Radiolite lamp based on dynamic chaos generator was developed in the conventional light bulb package. Here we can see several areas of application for Radiolite. Light in buildings and territories with the help of set of sources of incoherent radiolite that provides vision of these objects using radiometric equipment. Tapes and surfaces made of radiolite sources, for example, self-adhesive wallpaper. Walls of radiation receivers that provide high sensitivity and spatial resolution. Radiolite differs significantly from visible light concerning its propagation characteristics. This feature enables different vision, including transparent or semi-transparent walls. Radio garlands for objects, including moving ones, outlining, that could be applied for airplanes landing during rough weather conditions, mooring of ships during the fog, or railway and road transport. Here you can see the final result of the development of the developed ultra-wideband Radiolite lamp and its package. The output power of the lamp is 2 milliwatts and its frequency ranges from 3 to 5 gigahertz. Due to the noise-like incoherent nature of the radiolite, the addition of the signals from different sources occurs without interference. This fact makes it possible to create radiolite panel that consists of multiple independent radiolite sources, where the total power of the panel is the sum of its elements' power. In order to create radiolite images, we have to create radiolite light-sensitive element that is able to receive the signal and estimate its power. This element could be made using the analogy to the rod in eye. As a result, an experimental cell of radiolite receiver was created. You can see the radiation pattern of this receiver on the slide, as well as the receiver's main characteristics, such as frequency range from 3 to 5 GHz and its sensitivity up to 85 dBm. Now, when the radiolite source and receiver were created, one can proceed to image acquisition using Radiolite. In order to get some spatial resolution, we have to use directional antenna. Such antenna was developed in our institute and it is shown on the slide. It is parabolic antenna with horn radiator. Frequency range from 2 to 7 GHz. On the left figure you can see its radiation pattern and its width at -3 decibels level is around 10 degrees. In order to create a picture, we use mechanical scanning of the required area. This experiment with Radiolite was conducted in the conference hall. The red arrow shows the placement of the Radiolite lamp. On the bottom figure, you can see Radiolite image. Red spot corresponds to the Radiolite source, and two other spots on the sides of the image represents signals reflected from the sidewalls. After that, there was conducted an experiment concerning object detection using Radiolite imaging. 3 images in total were created. First one without any additional objects, second one was made when a person stood in the middle of the hall, and the last one was made when a person appeared near the sidewall. The bottom figures are the different images relative to the first image without objects. One can clearly see the presence of a person on the different images. Next series of experiments were conducted with multiple sources of Radiolite. On this slide you can see equipment and experimental scheme for Radiolite imaging with objects. There were used a total of 6 Radiolite lamps. Here you can see the result of the experiments. The upper picture shows the Radiolite image with Radiolite lamps turned off. We can see a significant level of noise here. The bottom figure shows us the picture of the hall when the lamps were enabled. One can see the uniform power of the signal in the whole area except for the 4 spots on the upper part of the image that correspond to the placement of the Radiolite lamps. Several objects were used as an object for the observation. They are a teddy bear, metallic cube with reflective surface, metallic cube with scattering surface, radio-absorbent material, and cuvette filled with water. Here you can see the result images for cuvette filled with water, images on the left, and radio-absorbent material. For each case there were created 3 images: the background with no object, image with the object in difference image. In the both sets of the image, one can clearly see the presence of an object only on the difference image. There are Radiolite images of the metallic cube with different types of surfaces, scattering surface and reflective surface. The signal reflected from the object for the reflective surface is higher than for the scattering surface, but in both experiments one can clearly see the object even without creating the difference image, unlike the previous case of experiments. There also was conducted an experiment where the image of the object was obtained when there was a 30 centimeters wall between the object and the receiver antenna. Under the photo of the cube, you can see the scheme of the experiment. The object was placed 2 meters apart from the wall and the receiving antenna was 1 meter apart from the wall. Here we can clearly see the object outline on the Radiolite image. So, this experiment shows the possibility of vision through the wall using Radiolite. The last series of experiments was dedicated to resolution of the Radiolite imaging. In these experiments, 2 objects with sketching surfaces were placed in front of the receiver antenna at a distance of 1.5 meters. The distance between the objects was 13 centimeters and 7.5 centimeters. On the slide, we can see images for both distances between the objects. On the difference image for 7.5 centimeters, we can still see 2 objects, but their spots begin to interfere. So, we can estimate that resolution of the system is around the average wavelength of Radiolight signal. This is all what I'd like to tell you. Thank you for your attention.